All right, welcome everyone to a wonderful quiz morning. So today we'll just do quiz 2 review, should be fairly straightforward. Also, I did a review of my lectures. Apparently I have a verbal tic where I say right like a lot. So, no one's noticed that, just me? Okay, well if I say right like too many times, just flag me down and tell me to stop. Because I had a prof with like a verbal tic like that, but his was okay, and it was so distracting that I counted how many times he said it during a lecture, and it was like 300, and I didn't learn anything that lecture. So I don't want to be that bad or distracting. But let's go on with quiz 2 review. So let's ask a forking question. Start the morning off with a bang. So consider this code. It's fork, fork, fork. So if you have a question like this will probably be beyond the scope of the quiz because it probably takes too long to write. But we should be able to do this. So what's one reasonable set of outputs? Assume the initial process has PID 2. Again, P is just a number to identify a process. And then other questions could be like, what order are the outputs in? How many times does that print statement even get executed? And what are the relationships between all the processes? So anyone off the top of their heads, how many processes are there at the end of this? Yeah, 8. Yep. Anyone disagree? And all their relationships? Yeah. The 4 in the parent? Like the parent has 4 children?
No, the parent process would create 4 more children from the second and the third 4.
Yeah.
And then the child of the first 4 would do the same thing. And then within that, the child of the second would create 2 more 4s. That's
Yeah.
how we get the 8, right?
Yeah, and then have the 8. So let's even break this down, give outputs to things, and just break this down as much as possible because this is somewhat involved. So let's go ahead and switch over. So our question was, we had main. I'll skip a few. Whoops. Equals fork. I'll skip some steps. Second equals fork. Whoops. Oh, and then I have my print statement. Print F, we know what it's going to print. Okay, so what's some reasonable thing that could happen? Well, initially we said we'll have process ID 2, and it will start executing main, so it's a process, it already exists, our terminal launched it or something. And then did exec VE, and we know what exec VE does and all that fun stuff. It's good to know. So on the first call to fork, we'll have PID 2. And it is going to create a child. So after the call to fork, we're going to have a new process. So this will move here, and then we'll have a new process probably called process 3, which will also be at the same point right after the fork. And the only way to distinguish them is the return value of fork, which is stored in first. So in PID 2, first would be equal to, we'll just give a number. So let's say we create process ID 3. That probably makes sense. So in the parent, first is going to be what value? 2, because that's the process ID of the child. So first would be equal to 2, and in the child, what would first be equal to? 0, because it's the child. So now we have both process 2 and 3 that could execute next. Which one executes first? Yeah. Sorry? Oh, yes, sorry. That was a brain fart. 3, like that. Yeah, sorry. It would get the process ID of the child, which in this case is 3. So thank you. All right, so now we have 2 processes right after the first call to fork. What order do they execute in? We don't know. That's the fun of this course, right? We don't know anything. So let's say process 2 goes ahead and executes, and it executes another fork. So process 2 executes fork, and it would create a brand new process. Here, I'll do this. PID T. So process 2 moves on to the next line, and it would create a new process, probably process ID 4, and it would be a direct child. So let's draw a line from there. Actually, I need more room. So in PID 4, what's first going to be equal to? Yeah, first would be 3. Because in process ID 2, before the call to fork, it has a variable called first. And when you call fork, it's an exact copy at that point. First already exists, so we would just get a copy of it. So first would be equal to 3 still, because it's a copy. And then the only difference between them should be the value of second. So in, let's say, in process ID 2, which created it, what's the value of second? 4. Anyone disagree? All right, in process ID 4, what's the value of second? 0. That's it. And now we have process 4 that's just sitting after the second call to fork. So let's just be boring and worry about another call to that process ID 2 makes. So process ID 2, let's go ahead and have it call fork again. So it's going to create another new process. So at this point, it would probably create process ID 5. What's the value of first? Huh? 3? Yeah, so it's a clone. First equals 3. What's the value of second? 4. Again, clone right before the call to fork. And the only way to differentiate them should be third. So what's the third in process ID 5? 0. What's third in process ID 2? 5. And then at that point, process ID could go ahead and we'd see something like we would see a print of first equal 3, second equal 4, third equal 5, and then that process would be done. So thankfully, we can go ahead and delete it. So we would erase it. And then also process ID 5 exists at that point, so it could go ahead and print its statement if we're so lucky with our scheduler. So we can go ahead and delete 5 and show its print line. So it would print first equals 3, second equals 4, and then third equals 0. So let's put a little check mark, check mark, check mark. So those are done. All right, so let's just argue about process ID 4 that's going to come in. So it's going to call fork, and it needs to do its third. So when process When process ID 4 calls this fork, it will create a new process that will be its child. Actually, I'll put on the other side and give it a bit more room. So it would probably spawn process ID 6, something like that. What's first equal to? What's second equal to? And then what would third be equal to? And then in process ID 4, what would third be equal to? 6. So now at this point, either could go ahead and print because it's all done now. So we'd have another statement where this would be for 4, first equals 3, second equals 0, third equals 6, and then we could also have first equals 3, second equals 0, third equals 0. So that means this is done, this is done. So we just have process ID 3 now. So process ID 3 is about to call its second fork. So if it calls fork, it would probably create process ID, what are we up to now, 7. So what would the value of first be for process ID 7? 0, because it's a clone. And then what would the value of second be? 0. And what would the value of second be in process ID 3? Cool. So now at this point, we will have process 3 here and then process 7 here. So argue about process ID 3 first. So if it comes, it would create a child, probably called process ID 8. What would the value of first be? 0. This should be getting fairly boring now. 7. And then what's the value of third? And then what's the value of third in process ID 3? 8. And then they can both finish and execute now. And then we just have to argue about 7. So 7 would come, probably create something called process 9 at this point. What would first be? What would second be? What would third be? Okay, and then what would third be in process 7? 9. So if we do all that, let's see. We have first equals 0, second equals 7, and third equals 8. So that's from process 3. Then process 7, first equals 0, second equals 0, third equals 9. There's that one. For PID 8, first is 0, second is equal to 7, third is equal to 0. And then for process ID 9, first is 0, second is 0, third is 0. And then there's a question, can you remind us why the last variable takes on the value of the child PID? So at the time of the fork, exact copy, and then the only difference is right after the fork, the return value of fork. So these are all the print statements we'd see. That's like a reasonable thing, and this is what our tree would look like. So yeah.
So there would be many different iterations of the print depending on if the child runs the fork before the parent.
Yeah. Yeah. Yeah, so the process ID would be different, but they'd be consistent along the processes. So, but the process IDs could be different. I just picked, you'd get random process IDs depending on what your OS wants to do, and then you can't determine the order of the print statements too because you have no idea. So all the IDs might be different, all the print statements might be in different orders, but they would be somewhat consistent with respect to whatever this tree looks like. And our tree is always going to have the same shape. So whatever the original process is has 3 direct children, which makes sense because there are 3 fork calls. And then the first child from the parent made 2, and then the other child made another 2, and then that one made 1. So this is what our tree would look like every single time. So any questions about that? So what could I do to, if I wanted to enforce some weird order between processes, what's one thing I could do? I could just wait. So if I stuck weights in here, you would actually be able to somewhat get an order. So should know what wait does. It just waits for that process to essentially call exit and die. Okay, so that is the forking question. So we're all good. That's probably harder than anything on the quiz, so that's good. So if you understand that, like, it's just getting used to fork. Fork just exact copy at the time of the fork, and then the only difference is the value of the process ID. So if this didn't hammer it home going like 8 times, I mean, it should be okay. All right, what about a threading question? So let's say we have something like this. We have a global variable int I, and we have 3 threads. So before any thread executes, we have I equals to 0, and then 2 threads execute I plus plus, 1 thread executes I minus minus. You don't have any locks whatsoever. What are all the possible values of I? All right, anyone want to tell me all the possible values of I? Yeah, pretty much anything from 0 to 1. Could I get
-1 to 2. -1 to 2. 2 to -1, right? 2 to -1. 2 to -1.
Yeah. Okay, so we think -1. No, we got a no. Okay, no -1. 0 at the end. Okay, we got a 0. 1, 2, 3. So we think it could be 0, 1, and 2. Okay. Well, let's see. So if we have this, we have 3 threads. So they only have 1 line each. There's no order. You don't know what's going on. What's I minus minus? Well, it's actually like a read of I, and then, you know, it goes to a register, and then we increment it, and then we write out I. So each of these threads would be doing essentially the same thing. Read I, inc, write I. I minus minus is a little bit different because it would do a dec instead. So, I mean, what value should it be if, you know, everything was atomic and everything was all great? 1. Okay, so we should be able to argue about what happens in the case of 1. So in 1, thread 1 could just read 0, inc it, so now it's 1, and then it would write out I, so it would write out I equals to 1, so now globally I equals 1. Then thread 2 could execute. It would read a 1, inc it to 2, and then we'd write out I. Then I would be equals to 2, and then thread 3 would come along, read 2, dec it to 1, and then write I. And now I is equal to 1. That would be the case if every thread just goes to completion. It's like all atomic. If it was like magically protected by a lock. That's what we would expect. All right, so how would we possibly get the value 2? Yeah.
Could thread 1 execute to completion, but then thread 3 executes, it reads, it reads, decrements, but then gets preempted by 2. It read, increments, goes back to 3, writes, and then goes back to 2 and writes.
That sounds reasonable. So let's see. So you said thread 3 starts executing?
It does the read and decrement, but then gets preempted by 2.
Yeah, so it would read a 1, then it would decrement it to a 0, and then now gets preempted. So thread 2 starts executing, and it would then read a 1.
It would increment.
So 2.
And then it gets preempted by 3 again.
Yeah, so 3, so within a thread, they have to execute in order. So if 3 just execute the decrement, it has to execute write, because within a thread, you still have to do things in order. So it would write out, so it would write out a 0. So now I is equal to 0. And then thread 2 would execute, and it would write out a 2. And now I is equal to 2. And then everything's finished. So 2 is possible. So let's see. So we have a 1 and a 2. So those are both possible. What about, what could happen to get a 0? Wait, where's my big eraser? Whoa, that's such a... So what would I do to get a 0? Yeah.
You get T1 and T2, I'll just say it in short, like to preempt each other and eventually just write a 1 and then 3 dice. So for example, thread 1
Can just...
increment preempted by thread 2, read increment, write, and then back to thread 1, write, and then thread 3 writes.
read 2, inc to a 1, and then so now I is globally, equal to 1. Whoa, that's a big eraser. And then thread 2 could go ahead, write I. So now I is equal to 1 again. And now in thread 3, we would read 1, dec. So now we have a 0. And then we would write out I. So now I is equal to 0. Okay, so now we think it could also be a 0. All right, so now we're done? Oh, so negative 1's possible. How would negative 1 be possible?
So like all 3 threads execute up to write, and then thread 3 write last.
Yeah, so all 3 threads could, so I equals 0. So we could have thread 1 execute read 0. It could do an inc to 1. Context switch thread 2 read 0. Incs that to 1. And then thread 3 would read a 0, decrement it to a negative 1. And then all we need is for thread 1 and 2 to write, doesn't matter what order at this point. So it would write I. So now I equals 1. Thread 2 would execute write I. So I equals 1 again. And then thread 2 would, thread 3 would execute write I. And now I is equal to negative 1. But no matter what, because we have 3 threads, there's going to be 3 writes to the global variable. We just don't know what they're going to be. So our possible values, negative 1, 0, 1, and 2. Anything else it could be? Yeah, we kind of covered the worst and best case. The most positive it could be is a 2, which is essentially we ignore the minus minus. And then the most negative it could be is a -1, which is ignoring the 2 plus pluses. So, but it could be literally any of those values depending on how unlucky we get. So that's why data races are fun. Right. Any questions about that? That's a data race. Yep.
Unrelated, what is the expected value? What are the percent chances that we get Can you predict that?
Probability.
You probably could.
Like 1,000 times. Like, do you think there would be a distribution?
There would be a distribution, but it would be specific to probably your kernel version and your actual CPU.
So if you did another 1,000 tests, would you get a similar distribution?
On the same machine, probably. But as soon as you move machines, it might be completely different. Or, you know, the next gen, Intel releases their next gen processors, they change something internally, it's all different. Or they change the kernel for some reason. Well, they change it all the time, so you update your kernel, your thing doesn't behave anymore. And that's why like some of these bugs you don't see them for like 7 years because it just works. And then someone changes something that should be unrelated, and then all your programs are now broken. So that's fun. Okay, so that was threading, forks. That's pretty much the hardest parts, and we'll just go through the rest of the stuff. Because the only other real hard thing was like the condition variable stuff. But let's quickly go through everything else, and I'll take other questions. So we saw way back, this is like lecture 4. These are just all the summary slides. How to create processes. So every process has a parent-child relationship. You only create new processes with fork. That's the only option you have. And then right before the fork, the processes are going to be exactly the same. After the fork, they're going to also be exactly the same, except for the value returned by fork. And the child, it's always going to be 0. And in the parent, it's going to be the process ID of the child. There's no exceptions there. That's what's going to happen. Unless fork fails, in which case your computer's probably dying, so don't worry about it. And then there are different processes. You're up to the scheduler. You can't determine any order, unless, of course, you wait, which would wait for one of the processes to actually exit. And at least on Linux, what are you only allowed to wait on? Your direct child. You can't wait on anything else. It's only your direct child. On like super old Unixes, you can wait on like grandchildren, but they quickly decided that was a very poor idea. And you can't do that anymore. So on Linux, it's only your direct child. So yeah.
What happens if you try to wait on a PID that's not, or well, let's say you call wait PID on something that's not your child.
So the question is, what happens if I call wait PID on something that's not my child? And the answer, let's see. Man, wait. So it sounds like something bad would happen, blah, blah, blah. So the value of options, that's options, Yeah, I wonder why people don't like reading documentation. Error, there we go. So it would probably be an error. Some of the errors are the file descriptor is non-blocking, process that refers to it is not terminated, so you're doing a non-blocking call. Then there's eChild, so the calling process does not have any unwaited for children, so you also get an error if you try and wait without children. You'll get an error if it is not a child or does not exist. So you'll just get an error, you'll get an interrupted, and then eSearch. Yikes. All right. Well, those are all the errors you can get. So if you try and wait on something that's not your direct child, you'll get an error. And I'll just be like, nope. But of course, if you don't check for errors, you might think it actually worked, and of course it didn't, and it's going to be bad. But yeah, you you have to scroll pretty far to find out what bad could happen. All right, any more questions? 4 children, all good. All right, so we were responsible for managing processes. This is where we actually learned about wait and learned about the state process that we're in. There were zombie processes and orphan processes. This is probably beyond the scope of the quiz for you guys because I don't think section 1 has gone into this in that much detail yet. But zombie process is just a process that's exited that hasn't been waited on yet. It can't free its resources because you need to call wait on it. And a orphan process is just, you can't tell what order processes are going to exit in. So if the parent dies first, then the child would still need a parent, so it gets reparented. Likely it would go all the way up to process ID 1, unless you're Linux and you do weird stuff. But for quiz 2, the focus is just on wait. If that is even the focus, it's probably not even going to be that big of a part, but you should know what wait is.
So what wait does is you put in the PID, then it waits for that ID to exit.
Yeah, so there's 2 versions of wait. There's wait, like the default wait, which waits for any of your children to exit, and the first one. Yeah, so if you call wait, you'll get the first child that exits, and you can also do wait PID to wait on a specific process. But wait would just return once when the first child dies. So in this case,
You wait for all children.
yeah, if I wanted to wait for everything, oh, okay. So this might appear initially to be somewhat correct. So is this correct?
No, because some process doesn't have 3 children.
Right. So wait only returns for one child dying, or sorry, on the first child. So if I call wait 3 times, it'll wait for 3 processes to die. And if we go back to
Maybe if we wait one after first, one after second fork, one after third fork, it will work. But not like together. Like one after the first fork, one after the second fork, and one after the third fork.
But like the child of the first
The child blocks.
yeah, so in this case, if I have 3 wait calls at the end, they would all execute after all these get set. So the only thing that can actually do 3 wait calls is PID 2. So PID 2 can do 3 wait calls and wait on 3 children, but the rest of them, if I don't check for errors and I do this, I mean, that'll happily execute and finish and everything because the first parent is going to wait for everything and be fine, and the other ones are going to wait for its children. But eventually, if it only has 2 children and it has 3 wait calls, the third one's just going to error. But we just don't check errors. So this is just going to wait for everything. But it's like
Hard.
totally not obvious. Yeah. Yeah, so yeah, the comment was, could I just put wait in a while loop and just go on and on until I don't have any children anymore? Well, that's exactly what a init does. Right, you just made process ID 1 because not only is it just going to go in a while loop while it's all out of children, if you get reparented stuff, if you just wait on all your children, that doesn't mean you're done. You might get new children later. So a init at the end of it, I wonder if I can see it. If you look at a init, it essentially will have a loop after it makes some processes. It'll have a loop at the bottom that says, while true, wait. Yeah.
Can you do, like after first, you have a variable called number of children, then after first, you check if it's bigger than 0, that means you have a children. Then you check, like each, then second, then third, you check if it's greater than 0. If it's greater than 0, you increment children. That way you know the number of children you have. Then you.
But so if you keep track of the number of children you have in a variable, wherever you fork, you're going to copy that variable. So you could do something, but you'd have to change that variable to be like, if I'm the child, I have to reset that to 0 and then keep track.
Oh.
So you can do that, but you have to be careful because it's a copy whenever it happens. So if you're the child, you have to reset yourself to 0 every time.
Is there a smarter way to make sure you can like wait for all children? Is there a command?
No, you just call what, if you want, you can see how many children you have by just, I think you can, there's a system call that will tell you how many children you have.
Oh.
But if you are a NIT, you might get new children. But otherwise, but you should know how many children you have anyways.
Should be no easy.
Yeah, I mean, you're the only one that creates children, so you should be able to keep track of it. Okay, any other questions? All right, then we saw IPC, which isn't going to be covered anyways, but that was like read and writes, lots of fun with file descriptors. That was good fun. Signals, there might be a little bit about signals, but not really. There might, actually, why am I telling you what's actually on the quiz? Not that important, very, very minor. There's a 4-question go over this. All right, then we saw threads. We explored them to something we already know, processes. So they're just essentially the same thing. The only difference is what address space they're in. Threads are all in the same address space. Then processes are completely separate. So threads are lighter weight, share memory by default. That's generally the big thing. And a process can have multiple threads, but whenever it starts, it just has one. Yep.
Let's say a program has multiple threads. I think I remember you saying this a while ago, if a signal comes to the program from the OS.
Yep.
It's not like a strict reason as to who gets the signal. It's just a thread gets the signal.
Yeah. So if you have kernel threads, and say you have like 8 kernel threads running in your process, and you get a signal, there's like various things that could happen. You could get a signal, you could have to handle the signal on every single thread, or what the kernel does is like, oh, well, one signal, one interrupt, and it'll just interrupt a random thread.
What's the difference with users? You said kernel threads, they're different with user threads.
Yeah, so user thread, the kernel doesn't know about it. So like in your lab, was it lab 3, where you're using signals? There's only one kernel thread, so you know what it's going to come in on that. Yeah, there's only one, that's the thing that will handle it, which is why in lab 3, if you disable interrupts, or if you disable signals, you won't have concurrency. Right, because you only have one kernel thread. The kernel doesn't really care about what's going on. And if you say, I don't want to listen to signals, you'll ignore them. Okay, then we saw the difference. Yep. So are the labs on the quiz? No. So like the concepts of like threads and stuff and like what they would do, perfectly valid. Implementation, no.
So like we wouldn't be expected to like, for example, write different types of blocks. But we would be expected to like read a code statement that has implementation for locking C, of course.
Yeah, you won't have to write any code. You'd have to read code, and you might have to suggest changes or be like, hey, this is broken. This is what you should do. Okay, so that was, user threads, kernel threads. Funnily enough, actually, why the hell am I saying what's on it? This isn't terribly important. But now we have synchronization issues, which are important. So then we got critical sections. This was just using mutexes. So we saw,
Sorry, I just want to, I forget if it was mentioned. What happens if you have a bunch of threads in a process and it forks?
Yeah, so that's another thing. So what happens if you have a bunch of threads in a process and it forks? So whenever a fork happens, it clones the calling thread and the calling thread only. So the new process will have a single thread in it. That's a clone of the exact thread that called fork. But that's also a headache because say I have 8 threads and one calls fork, and I want like a consistent state at my fork. If I have 7 other threads monkeying around with memory, I have no idea what state that's going to be in. So there's actually like a p thread at fork where you can control what happens. So you can say, hey, all threads like join or do something. So I know what memory looks like at the time of the fork, but that's like super, super advanced.
Do we have to worry about that?
Aside from that, the only thing that would be reasonable in this course is to ask you of that fact. Like at fork, what happens? It clones a calling thread. Yeah. Yeah, because whenever you make a new process, it's just one thread.
And that's for kernel threads, right? If you have user local threads, it would just clone.
Yeah, it would just clone the process because it doesn't know about them, so it would be in whatever state that happens in, which would, if it's only a single thread, it would actually be consistent though, right? Oh, I said right again. God damn it. Okay, so you could fork your lab 3.1 and it would generally work. So, so yeah, we saw mutexes. That was the main way of locking and ensuring mutual exclusion. They were this most straightforward lock. And yeah, they weren't too interesting, but we saw how they prevented data races. We need some hardware support to implement that. That was generally just for your labs. And then some kernel support. You saw you did your own wake up and signal. So implementing that, not a problem, but essentially the condition variables, how you would use them, probably is a problem. And then we saw a read-write lock. The other section did not go over read-write locks, so they're just kind of a performance thing. Then we use semaphores, and they just contain a value. It's like an unsigned value, and you can either increase it or decrease it, and the rule with decreasing it is it will never go negative. So if it's 0, it's going to sit there, block, wait for some other thread to increment it, so then it can safely decrement it. And that's it. So that was mostly for ensuring some type of order between threads. But then we also explored that big producer-consumer example, which was great stuff. And then we saw condition variables, so they're generally clearer for complex signaling conditions. And then we also saw like locking granularity matters of like the extent of your locks when we had that parallelization example and we locked the whole thing. It worked, but it was slow. And then we saw we had deadlocks and bad things happened when we had deadlocks. Yeah, so any final questions? So I'll be on Discord. Ashley and I will be on Discord during it. Format, true, true, false, true, multiple choice, and then 2 short answer. They're going to be much longer this time though, so be very careful. Just spend time. If you have the extra time, just do the question again. Like 1 minute, true and false, should be fairly straightforward. And then 10 minutes for each multiple choice. Probably similar to that threading one. That was pretty good. The forking one was pretty good. Then some short answer, you know, how would I do this? And then 15 minutes for a final short answer, and then that's pretty much it. We can go ahead and, what lecture was that that had good stuff? Yeah, so the producer-consumer example, so, oh no. Yeah, yeah, so like the condition variable stuff. Do we kind of remember this consumer code? No? Yeah.
What does the sem try weight do again?
Sem try weight. Oh, so that's essentially tries to decrement the center for. So this is not meant for synchronization. That's just meant so I can record how many times the loop needs to execute. So that's like an internal thing just to simulate producer-consumer. So the only code we actually need to care about is like, whoops, is that. So this was the condition where we wanted to wait on an empty slot. So if everything is filled, we want to wait on an empty slot. And then in the consumer that empties the slots, it would signal anything that's waiting for an empty slot, because now we change the condition. There's now at least one empty slot. So it could wake up the producer, which is essentially will wait, put itself in queue if all the slots are filled, and then wake up. So any questions on this? Because I think we had a question before where we screwed this up a little bit, where we replaced the while with an if or something like that. And was that bad? Yeah.
Use well because it just might wake up for some reason, right?
Yeah, it might have a spurious wake up, which I think is, for the context of this course, assume that doesn't happen. If there's a third thread, yeah, but you might wake up too, and something woke you up, and then before you reacquired the lock, another thread got the lock and then did the thing, and now the condition's false again. So you would want to put yourself back to sleep and recheck it. And if you have an if, you would assume that it's true, and then you're screwed at that point.
Is this the example for a condition variable or center for?
This is condition variable. So the center for here I only use for keeping track of the number of things to produce and consume. Yeah, so let's see. Any other last minute questions?
We talk about the syntax again for the conditional variable.
The what?
The syntax, the system call syntax.
For the condition variable? So for condition variables, so essentially you only have to care about the wait and the signal. So wait, you have to call it while you have the lock, and then it essentially will put yourself in the condition variable. You can think of as just a queue. So it will put you in the queue and then put yourself to sleep and unlock the lock. And then whenever something signals you, the first thing internally that would happen is you would grab the lock. So you would have the lock before and after the wait call, and signal will just wake up one thread, broadcast will wake up every thread that's in that queue, and that's pretty much it. Yep.
I think I remember you saying this, I just want to make sure, but we need to pair a lock with every CV's got to keep securely at itself to the queue, right? Because that's a global.
Yeah, that's one way of thinking about it, but it also has to reacquire the lock at the end of it too. Yeah.
And the condition and the consumer and producers share the same log.
Yep.
So only one of them can have it.
Yep. Yep. Yep.
Will there be any multi-selects?
No, we deleted those because Quarkus was like, "Hey, you get 0." Yeah. So the way Quarkus does is, if it's a multi-answer one, it takes like the total points for that answer, divides it over the number of correct answers, so it like varies wildly depending on the question. And if you select an answer that's wrong, it's negative whatever that point is. And if you select it right, you get that. So if there's only one right answer and you select one right and one wrong, you get 0. If there are, 4 answers and 5 total possibilities and it's worth 4 marks, each one of those is worth 1. And you can, it's like totally out of whack, right? So we just got rid of them. And yeah, right now there's only one correct answer and a lot of choices.
How much is the long choices? 8.
What is it, like 16? Well, well, you pick one of the 16.
Only one of the 16 options?
Yeah.
If we do it okay, is it like obvious which one of the 16 it is?
Yeah, it's the right answer.
There's no way to gamble. Have to find it out.
Or you should just be like.
Yeah, like.
Or it's gonna be like funny iterating. 16 is section of the code, right? Or it's gonna be like a separate question.
They're like separate questions. Like each multiple choice is a question. Oh, I guess we have to wrap up. But if you followed the examples today, you should be okay. All right, so good luck. I'm pulling for you.